simple circuit, just a battery, a wire, and a light bulb. Nothing seems to be happening. It looks completely still, but is it really?
Suddenly, tiny charged particles appear and start rushing through the wire. These are the electrons, the real heroes of every electrical circuit. They carry energy from the battery all the way to the bulb. This movement, this flow of charge, is what electricity actually is. And in this video, we are going to understand exactly how it works, what pushes these particles, what slows them down, and how we measure all of it. When charge carriers move through a wire, we call that flow electric current. Current tells us how much charge passes through a point in the circuit every single second. We measure it in amperes, named after the French physicist André-Marie Ampère. Think of it like a stream of water. If only a few particles are moving, and they move slowly, we have a low current, but if many particles rush through quickly, the current is high. More carriers moving faster means more current. We can plot current over time on a graph. When nothing changes in the circuit, the current stays constant, a flat, steady line. This is called direct current, or DC. The height of that line on the graph tells us exactly how strong the current is. Mathematically, current equals the amount of charge that passes a point divided by the time it takes. Delta Q is the charge, measured in coulombs, and delta T is the time interval in seconds. 1 ampere means 1 coulomb of charge flowing every second. So we know that charge carriers move through a circuit, but what makes them move in the first place? The answer is voltage. Voltage is the electrical pressure that pushes charge through the wire. It is measured in volts, named after the Italian physicist Alessandro Volta, the inventor of the first electric battery. Imagine two batteries, one small, one large. The small battery produces a low voltage. It gives the charge carriers just a gentle push, so they move slowly through the circuit. The large battery produces a high voltage. It pushes them much harder, and they race around the loop at high speed. Same wire, same carriers, only the voltage is different. On a graph, voltage over time looks just like current for a steady source, a flat, horizontal line. A higher line means a higher voltage, more pressure pushing the charges. A lower line means a lower voltage, less push, less flow. The battery is what sets the height of that line.
Formally, voltage is defined as the work done, the energy transferred per unit of charge. W is the work in joules and Q is the charge in coulombs. 1 volt means it takes exactly 1 joule of energy to move 1 coulomb of charge from one point to the other. Voltage is always measured between 2 points. It is a difference, not an absolute value.
We have charge carriers moving through a wire, pushed by voltage, but not everything in a circuit lets them pass freely. Some components, like resistors, get in the way and slow them down. This opposition to the flow of current is called resistance. The higher the resistance, the harder it is for the current to get through.
Think of it like a wide pipe versus a thin one. A low resistance is like a wide, open path. The charge carriers move through quickly and easily. A high resistance is like a reduced, limited passage. The carriers face more difficulty getting through, and fewer of them make it past at any given moment. Same voltage pushing them, very different results.
If we keep the voltage fixed and increase the resistance, the current goes down. On a graph with resistance on the horizontal axis and current on the vertical, this relationship forms a curve that drops as resistance grows. Double the resistance, and you get half the current. This inverse relationship is one of the most important ideas in circuit analysis. Resistance is measured in ohms, represented by the Greek letter omega. The standard symbol for a resistor in a circuit diagram is a rectangle, and resistance is defined as voltage divided by current. R equals V over I. A resistance of 1 ohm means that 1 volt of pressure produces exactly 1 ampere of current. We now have 3 quantities: voltage, current, and resistance. And it turns out they are not independent. They are locked together by one of the most fundamental laws in all of physics. Ohm's law states that voltage equals current times resistance, V equals I times R. This single equation connects everything we have learned so far. A useful way to remember, Ohm's law is the voltage triangle. Place V at the top and I and R side by side at the bottom. To find any one of the 3 variables, cover it with your finger and the triangle shows you the formula automatically. Cover V and you get I times R. Cover I and you get V divided by R. Cover R and you get V divided by I. 3 formulas, 1 triangle. Let's see Ohm's law in action with our circuit. First, if we increase the voltage while resistance stays fixed, the electrons move faster. The current goes up. More push means more flow. Second, if we increase the resistance while voltage stays fixed, the electrons slow down, the current drops. More opposition means less flow. Voltage and current move together. Resistance and current move against each other. Finally, the graph of current versus voltage is a straight line. This is the visual signature of Ohm's law. As voltage increases, current increases proportionally. That's what the straight line tells us. The slope of that line is 1 over R. The steeper the line, the lower the resistance, and the more current flows for every extra volt you add. Let's put Ohm's law to work with a real example. We have a 12-volt battery and a 5mm LED. The LED has two key specifications. It operates at a forward voltage of 2 volts and it draws a forward current of 20 milliamperes, that is 0.02 amperes. If we connect the LED directly to the battery, the full 12 volts would push far too much current through it. We need a resistor to limit the current to the correct value. The question is, what resistance do we need? Step 1. Find the voltage that the resistor must absorb. The battery supplies 12 volts total. The LED takes 2 volts for itself, so the resistor must handle the remaining 10 volts. Step 2. Apply Ohm's law, R equals V divided by I. The voltage across the resistor is 10 volts. The current through the circuit is 20 milliamperes. 10 divided by 0.02 gives us 500 ohms. That is the resistance we need. We place a 500 ohm resistor in the circuit. The resistor absorbs the extra 10 volts and delivers exactly 20 milliamperes to the LED. The LED receives exactly what it needs, no more, no less, and activates at full brightness. The charge carriers flow steadily through the loop, the resistor does its job, and the LED operates safely. But what happens if we remove the resistor entirely and connect the LED straight to the 12-volt battery? With no resistance to limit the current. The full supply voltage is applied directly across the LED. The current surges far beyond 20 milliamperes. The LED cannot handle it and it fails instantly. This is why the resistor is not optional. It is the component that keeps the circuit within safe operating limits. Let's bring everything together. Voltage is the electrical pressure that pushes charge through a circuit, measured in volts. Current is the flow of charge past a point every second, measured in amperes. And resistance is the opposition to that flow, measured in ohms. 3 quantities, 3 units, 1 circuit. And connecting all three is Ohm's law, V equals I times R. This single equation is the foundation of circuit analysis. From it, we can always find the missing variable, whether it is voltage, current, or resistance, as long as we know the other two. The triangle makes it easy to remember all three forms at once. In a real circuit, these 3 quantities are always present and always linked. The battery sets the voltage, the resistor limits the current, and the current that flows is exactly what Ohm's law predicts, every single time without exception. That is the power of a physical law. It always holds in every circuit under every condition. That is all for this video. You now understand voltage, current, resistance, and how they relate. These are the 3 pillars of every electrical circuit, from a simple LED to the processor running inside your phone. Keep building, keep connecting, and remember, every circuit tells a story. Now you know how to read it.